right, in this video, we're going to talk about the concept of continuity. So, if you were to ask somebody in a class before calculus, what is continuity? What does that mean for a function to be continuous? The sort of common sense reply to that is usually going to be, well, if I have a function that is continuous, that means that I could draw the graph of that function without really lifting my pencil or my pen off of the page, which is a good way to think about it. But in our class, we're a little bit more specific, a little bit more technical. So if we have a function and we're saying that it is a continuous function at a point, x equals c, that means two things. Now, some people break this down into three things, but you really could look at it with just two sort of necessary conditions. Number one, your limit as you approach c has to exist. Now, that means the limit from the left and the limit from the right are the same. So we've talked about how we find limits, a couple different ways, but we need that limit to exist. So as we approach c, the limit of my function has to exist. If this doesn't exist, I can stop right there and say, sorry, my function is not continuous. The first thing I need isn't true. If it is true, the next thing I want to make sure is that my function value, so f of c, is equal to my limit value. So some people break this into multiple parts, like I said, but I think it's efficient just to think of it in these two ways. So whatever that limit is the same as my function value. As we've seen before, we can't have a limit at a point where our graph has a hole in it, or it has a hole and then the function value is somewhere completely different. In that case, we would not have a continuous function. We would say that it is discontinuous. But if these two things are true, if my limit exists and the limit is the same as the function value, we say that my function is continuous at that point. Now, if we're continuous on an interval, say from x equals 1 to infinity, we would say that my function is continuous on that interval. So it's continuous at every single point in that interval. If we take a look at, say, this graph, this is one that we found a limit of when we first talked about limits. Here, this would be continuous on the interval from -7 up to 8, not including either one of those, and then continuous from 8 off to infinity, not including the 8. That's because I've got a hole in my graph at -7. However, if I go to the right of -7, I have limits which are equal to the function values. In other words, I could draw the graph from -7 to 8 without lifting my pencil or pen off the page. But once I get to 8, if I want to draw the rest of my graph, I do have to lift my pencil or pen off of the page and then pick back up at that y value of a 3 and then draw the rest of it. Now, you can obviously tell this point right here at positive 8, that would be discontinuous. Now let's think about that. I have the reason why it's discontinuous is the first condition. If I'm looking at 8, as x approaches 8 from the left is not the same as it's not the same limit as x approaches 8 from the right. So it does not satisfy the limit existence. In other examples we'll see in class, as I mentioned before, you could have a hole in the graph. That's going to be one type of discontinuity. Okay, so that is discussing the continuity of this particular function there. Now, what kinds of discontinuity could we have? Well, the first kind is going to be what we call a removable discontinuity. Think back to pre-calculus. This would be when you're looking at a hole in your graph. That's when you have a factor that you canceled from the numerator and denominator. So this picture down here looks like x sub 0. Nothing really different about that. That's just a subscript to that thing. If I look at that function value, it doesn't exist there. But I do have a limit as I approach x sub 0. So this is what we call a removable discontinuity. It's just a hole that if I were to fill in, then I would have continuity. Think about the difference between that and this one here. This is called a jump discontinuity. Even if I were to fill in the hole, either on the function coming from the left or from the right, I would not have continuity because there's a jump in the y values. So first type was a removable. The second type of discontinuity is called a jump discontinuity. This is typically where your function stops and then picks back up somewhere at a totally different y value and then keeps going. And then another type of discontinuity is called a infinite discontinuity. Some people call these asymptotic discontinuities because this is where you have your vertical asymptotes, like from precalculus. So it's not continuous here at x equals 4 because I don't have a function value at x equals 4. If I don't have a function value, I can't really have a function value equal to a limit, assuming that our limits are finite values. We'll talk more about that later. Okay, so we'll talk about continuity at endpoints. So just as a sort of overview, we have three types: infinite discontinuity, jump discontinuity, and removable discontinuity. Okay, so what about at the endpoints? So um, this one is kind of tricky here. In fact, I meant, oh yeah, this is what I wanted. If I go to -7, we said that this function is not continuous at x equals -7 because it's got a hole there and there's no function to the left. So there's no limit, there's no function value. But what if I were to fill that in? So if I was to fill that hole in at -7, is it continuous? Because I don't have a graph to the left, so I can't really do a limit from the left. It wouldn't really make any sense. But I do have a limit from the right. If I approach -7 from the right, it looks like my limit would be a 4. And the function value is a 4. So it almost seems like it does satisfy the definition of continuity if I'm only thinking about a one-sided limit. So at endpoints, if my function stops somewhere, if the endpoint is filled in, quote unquote, then usually I'm going to have continuity. So one way to state that would be if my one-sided limit exists and equals the function value at that endpoint, I do have endpoint continuity. So let's say that I'm looking on the interval from A to B. So I have a left endpoint of A. Or I'm sorry, it actually should be I think I mixed these around here. It should be a plus on the A and the minus on the B, because if it's a left endpoint A, that would mean that coming from the right, because the left endpoint means I stop at the left, etc. So if you want to mentally put a plus where that minus is on the A and a minus where that plus is on the B. I thought I fixed all my typos, but I guess not. Basically, if you've got a one-sided limit, that is the same as the function value at the endpoint. You have what we call endpoint continuity, which means if I was to describe the continuity in interval notation, I would use some brackets versus some parentheses. We'll talk more about this in class, but you should have plenty of information to get started on those questions in Schoology.